All right, so we got we got about 2 minutes or so before the class starts. And I just want to confirm that my voice, does it sound about right? Because I just changed my headset again. I just want to make sure that this headset works okay. Good day. Okay, great. Thank you. No audio in the last video. Okay. That's probably because the sound setup in Discord is entirely independent to the sound setup in OBS, and I probably did not look at the audio mixer signal when I used Discord. I mean OBS. So OBS is feeding to YouTube as a DVR, and then Discord is entirely independent. Having its own settings. So today I think I double checked and make sure that the OBS sound is also recording, because I'm looking at the meter and it seems to be fluctuating correctly. All right. Okay. We got about another minute or so. So, today is the last day before the assignment is due on Thursday, because, I want to be able to use Thursday to help explain the solution of the homework assignment, in addition to potentially talking about something new. So if you have any questions about the assignment, today is a very good day to ask those questions. Hopefully everybody is already somewhat in progress with the last homework assignment of this class, which is the tree traversal program. All right. All right, 10 seconds to go. Yeah, I had to change my headset because my other headset that I used was pinching my ears a little bit too much, because those are the on-ear type of headset, and they were just kind of putting too much pressure on my ears, and so I'm switching to a not on ear. This is kind of like, is it called circumaural? It's around the ears, so it's a lot more comfortable with this. All right, so it is 5:30, so we are officially getting the class started. So as I mentioned before, before the class started, today I just want to see if you guys have any questions about the homework assignment. So if anyone has a general question about a homework assignment, not so much, why is my specific program not working, but if you have a general question, it can be a concept question, like, how is a pointer used? How do we address a particular member in the structure? Or how do we deal with a double pointer, that sort of thing? Or you can say, well, my program is not working. Okay, how do I start to troubleshoot it? So I think, that probably is something that some people may have experience with. Okay, so RJ has a question, which is, talking about using a member of a structure. Okay, so the best way to talk about this, now that I got my tablet set up again, is to use a picture. So let me switch to, okay, I guess I don't have one already up, so I'm gonna start one. So I'm gonna start a journal, okay? So this is a general concept discussion, which was somewhat illustrated using sample programs from previous classes, but I did not have the tablet fully running in some of the classes. So today we can actually use a picture to do this, and I think it's probably best to use a graph paper type of setup. So let me change to a graph paper. So this way we can display the memory a little bit better. And I'm gonna wait until Joshua is done typing, because if the two questions are related, I can try to address both questions at the same time. Okay, will I also do a review of the double pointer? Okay, sure. Is it always an address per pointer? Okay, so we'll talk about that too. Okay, so first thing first, we'll talk about what a structure looks like in memory. Okay, there are two things that are really related. The program that I gave you guys last time, which is a TTP ASM, that contains the global variable structures. That is really helpful too. So let me just kind of go back and retrieve that from the previous class. I think it's pinned already as an attachment. Or maybe the one before. Okay, so that's actually on the 28th, maybe. Let me check. That's the Fibonacci program. Or is it in Canvas? I cannot remember. There are too many places for me to hide my stuff. Okay, let me switch back to today's text channel. Yeah, 3.3.c, it is an announcement. Okay, but I also posted an assembly, a TTP ASM file, probably on the same day. So let me go to Canvas and see if I can find it over there. All right, so C code, that's from the 28th. Okay. So I'm looking at the 23rd. Did I post anything on that day? Yep, I posted something. It's called alloc.zip. It's for allocation, but it is not the code for the homework assignment. Yeah, f.ttp-asm, I think that's just Fibonacci. So I could be wrong about that, but I distinctly remember that I worked on the assembly language code for the traversal program, and I got the tree already initialized. Okay. The tree.c is already done. I know that. But tree.c, that's coming from the announcement. So go check the announcement in Canvas for tree3.c. That's the C program. So that's for wine. Yeah, I definitely work on the TTPSM version of the tree, but I may not have posted it. So that means you can probably retrieve it from the website. Oh, you know what? That's one place that the one last place to find it is, if it's the last thing that I worked on, it will still be in the assembler. All right, there we go. Excellent though. Okay, so you guys already have access to it. It is still in the assembler. Cool. Okay. So this is important because this is the code that you should use as a basis to start to work on your program. Okay, because it gives you everything that you need as a shell, except for putting your code into here. Okay, on row 11. That's basically where you want to insert your code. Now, I do not want you guys to edit your program inside the spreadsheet, because that doesn't work. So you want to copy and paste, this code, in column A, and put it into something like Notepad. Okay, or if you have NeoVim, you can use my syntax highlighter as well, but that's definitely not needed. So this is a good starting point. So what I want to do, because RJ was asking about accessing structures, so if I go to the Assemble tab and look at the global variables that are initialized, okay, which is down here. Okay, so you can see that this is N1, which is equivalent to N1 in the C code. Okay, and we can see how the three members are, are arranged. The first member, which is the value, is having a byte of value 5. And then the second member is, I think this is the L, okay, and this is the R. So basically we are, the members are really just using contiguous memory locations in the case of the TTP, in the case of the toy processor, because the toy processor is a byte-wide type of memory system. So this is why they are just arranged like that. And this was talked about in a previous class, even though the voice may not be there, but it was actually discussed in a previous class. So, but you don't want to make the assumption, okay? So once again, do not make the assumption that byte 0 of a structure is always value, and byte 1 is always the L member, and byte 2 is always the R member. Okay, so do not make assumptions like that, and instead, what you want to do is to make use of the label definitions that I have done up here. Okay, so let me go back to the source, which is easier to view when we just want to look at the definitions. So when you look at line on rows 1, 2, 3, and 4, those labels are defined specifically so that you can use label definitions to tell you the offset from the beginning of a structure to get to the value as a member, to get to L as a member, and also get to R as a member. Now these label definitions has to match the C code, and it also has to match the way I initialize the global variables over here. But as long as the definitions here is in agreement with how I initialize the global variables later on, your code is insensitive to whether I change the order, or do I insert a new member, or do I just add additional stuff as far as the nodes are concerned. So you don't want to make assumptions about which one is the first, which one is the second, and which one is the last, and instead make use of these label definitions to get to each one of those. Okay, so this is from the perspective in the assembler, and let me just switch back to the assemble tab to go to the initialized variables. So what I want to focus on is actually really just the memory locations over here. So byte 5 is at location 2.1. At location 2.2 is the L member. So the L member is a pointer to another struct node, which is at location 2.4. But if you go to location 2.4, it is the value or the first member of another structure, and then the next one is the L member, and then the next one is the R member. So once again, do not make assumptions that the ordering of these things would remain the same, okay? Because I want you guys to write your code that is insensitive to restructuring members inside the structure. So so do not make the assumption. Okay. Do we have any questions at this point? The labels are specifically line 1 to 4. RJ, those are the labels. And I think the lecture before last week also talked about how to use the labels to get to individual members. So you might want to check out the lecture on the 28th. So even though the lecture on the 30th may not have the voice, but the one on the 28th does, and it also covers the same kind of topic. Okay, so this is from the perspective of the assembler. But if you want to look at everything from the perspective of, okay, I'm looking for my stylus because I keep losing it. Darn. All right, so give me a moment to locate the stylus, because without the stylus, it becomes a little bit harder to draw pictures in Zernal. And I definitely just used it earlier. Oh, nope. All right. Well, if I cannot find it, I'm gonna have to talk about this without using the stylus. But basically, when you look at the assembler, that really kind of tells you, how to make use of the labels. Um, this is the value, this is the L member, this is the R member, but do not make assumptions about, first, second, and third, and instead, you refer to the labels. So the way the labels are defined, okay, if anyone wants to find out how a label is defined, you can go to the sim tab. I know this is really difficult to see, but you can see how node value is having an RPN of 0. That's its value. This is the 0 is the value of that label. And then node underscore L has a RPN of 1. That's the value of the label node underscore 1. And then node underscore R2 underscore R has a value of 2. That's because its RPN member is 2. So make use of the labels. Do not refer to the constants 0, 1, or 2. Do not use just fixed increments and decrements to get to those individual members, and instead use these mechanisms to do it. The sample code that I shared on the 28th definitely has mentioning of how to make use of labels to access individual members. So I think that addresses the question. And then now I'm moving on to Joshua's question, is how do we use a double pointer? Okay, so the important part is to understand the C code first, okay, what a double pointer is. And then the other thing, so let's go to the C code, which we kind of illustrated last time using the debugger. So you want to kind of download that code and then run it inside GDB. Is that kind of what the class wants to do in general? Is to kind of review how the C code makes use of a double pointer. Because the concept is the same whether we are using an 8-bit architecture or a 64-bit architecture. It's the same concept. It's just that one pointer is wider than the other one. Okay, can I illustrate it? Let me see. Yes, I can illustrate it. Okay, so to illustrate this, once again, I need to go find my stylus, which I have misplaced. Given just a few minutes, I can misplace my stuff. Looking for it. Looking into my pocket, cannot find it. All right, so it's okay, I can still illustrate it. Hot gluing, yeah, there we go. All right, so this is not for this class, but I'm using the spreadsheet the same way. Okay, so let's look at memory locations. Okay, so this is kind of a simulation of what your program would do. So we have location FF, FE, FD, FC, and we did this analysis last week too, is to figure out what memory location would contain what, and so on and so forth. Okay, so you can even without the voice, I mean, you can still kind of make out a certain portion of what I mean by that, especially toward the end of last week's lecture, last Thursday's lecture. Okay, so when you look at the C code, okay, so the first thing for me is to download the C code again, or I can just view it online. That's fine. Okay, so when we look at the global variables of main, it has an array of 5 bytes. Those are the unsigned bytes. So those 5 bytes will occupy these 5 locations in main. Okay, and main, by the way, is already done. The assembly code, the TTP ASM code is in the assembler right now. So you might want to copy that before we change it to anything else. So go ahead and copy and paste that code into your editor. So these 5 bytes, would be array 0, which is here. So this is the byte corresponding to array 0, and this byte would correspond to array 4. And then the byte below that is going to be PTR. So PTR is initialized to point to the beginning of array, which is at location 0xFB. So when you look at the content of 0xFA, it should have a value of 0xFB. Okay, so when we look at how the parameters are pushed, you can see when we call traverse, PTR is the address of PTR is pushed first because it is the second argument. So that means this location, which is F9, is corresponding to the second argument to pass to traverse, which is the address of PTR. But the address of PTR is FA itself, and then the N1 is being passed to traverse, or the address of N1 is being passed to traverse as the first parameter. So to look it up, in the assembler, this is where we can find the exact location, at least the way the program is written at this point. So when you when you insert additional code into traverse, those offsets will change. But at least the way it is right now, when I look up N1, okay, so when I look up N1, it is at location 21 in hexadecimal. So if I go back to my memory map here, this is the address of N1, but in the assembler, it is at location, once again, I forgot, 21, okay, so 21 is over here. So this is how you can expect the stack to be set up when the subroutine gets control. When traverse first gets control, this is what you can see, this is what you can expect on the stack. These 5 bytes are not initialized. So that means, because when we reset the processor, all memory locations are reset to 0. So those 5 locations are very likely to be 0 because, you probably start executing the program after a reset. Okay. And then these 3 locations would be FB, FA, and 21. And you can see how location F9 has a value, which is FA, which points to the pointer. Okay. Now, you also have to kind of make the distinction of who is supposed to be to see what. Okay. The first and then the next location is the return address, which we are not too concerned about. Okay, so this is the return address to main. So when we return to main, that's going to be the byte. Okay. So as far as the subroutine, the first invocation of traverse is concerned, these are the 3 locations that it is supposed to access. It's not supposed to access anything above that, not directly, only indirectly. Okay, so when you look at these 3 locations, it would correspond to the first invocation of traverse. Okay, and I can turn on paragraph wrapping. Let's see, where should I go? It is probably in text, wrap text. There we go. All right. So these 3 cells are corresponding to what the first invocation of traverse should be able to see. And these 6 cells over here correspond to things that are actually in main. So if I want to specify it, this is for these are main's stuff. There are 6 bytes to it. So is that answering the question? Is that answering Joshua's question of how to use a double pointer? Kind of. Okay. So let me just kind of point that out again. So when you look at location F9, that is where the double pointer is located, because that corresponds to the parameter called array of traverse. It is a double pointer because the first thing you need to do is to look at the value at that location. That will give you the address of something. But it is the address of what? Okay, it is the address of another pointer. Okay, and then this pointer, which belongs to main, points initially to the first byte of the array that is in main. But this value will change. Okay, if you implement the subroutine correctly, this pointer will change, but it is being changed indirectly by traverse, because each invocation of traverse has the double pointer. So it knows where the pointer is, and it is capable of changing that pointer. So if you want to change the value of array 0, do you increment the double pointer? What do you think? Because I think your question is answering your own question. Well, okay, that your question is its own answer. That I should put it that way. Why do I want to increment a pointer when the objective is to change the value of a location? Oh, I found my stylus. It's on the floor. Yay. Okay, I'm gonna wait until all the typing is done. Okay. Okay, all right. Joshua is asking, so we use the double pointer to keep from moving the original pointer away from the start of the array. Well, each invocation of traverse has the same double pointer, and what it is going to do in the C code is it is going to increment what the double pointer itself is pointing to. So that means the value at location F9 is the one that is this is the start. Okay, this is where each invocation has access to. So we use this to locate this, and then this is the one that is incremented after we change the location that it points to. And then Alex says, with a double pointer, star array will always point to PTR. So not star array, it is just array. Okay, so we are not double dereferencing it. Array as a parameter in traverse is always pointing to PTR, not the address of PTR. It always has the address of PTR. But PTR itself is free to point to different parts of the array in main, and that is correct. So throughout the execution of the program, if it is implemented correctly, then this is going to change to FC, FD, FE, FF, and so on. But the pointer as an argument to each invocation is not supposed to change. And then the locations, from array bracket 0 to array bracket 4 should also be filled up with the values of the nodes as we execute the algorithm. I'm just waiting for the typing to be done. All right, so Alex is getting it. Good. So I increment the double pointer. I do not increment the double pointer. I increment what the double pointer is pointing to. So look at the C code. Okay, the C code tells you what the assembly code is supposed to do, or the meaning, the semantics is in the C code. And then Joshua is saying, so the first pointer is to traverse the array, the second is to grab the value. Okay, so let's make it very clear which one is the first and which one is the second. This is the first parameter. It is a pointer to a structure which provides the value. This is the second parameter, which is a double pointer to an unsigned character. So this points to a pointer, which in return points to the location where the value of the structure is supposed to copy to. Is that okay? Okay, excellent. All right, cool. All right. So in your program, in your subroutine traverse, do not, make the assumption that you're changing location FA. You have to get to that location using what is on the stack as a part of the argument. Because if I change main and I add some local variables and change, all of these offset to somewhere else, if somebody is making the assumption and go like, oh, okay, that's easy, I just have to make the assumption the pointer is always at location FA, that program is not going to work. That subroutine will fail if I make any changes to main, and I reserve the right to change main, I reserve the right to change the structure, and I reserve the right to change how the structures are initialized. So your code has to be insensitive to all of those changes. Is that okay? Do we have any questions? No questions? All right. So let me ask, is there anyone, does anyone have a question about how to debug this program? Because, all of these questions are conceptual questions that will be very useful to start coding. But for people who have already coded for a while, is anyone running into a specific problem where you don't know how to debug your program? Print statements. Well, if this were in a different environment, print statements would work, but it won't, right? Well, okay, I take it back. We actually do have all kinds of print statements. The print statements, okay, is in the form of, you already know, the trace analyzer. The trace analyzer is the ultimate print statement approach because it basically just prints everything that the processor knows for each for the execution of each instruction. So when you go to the trace analyzer, okay, which I think is a really useful tool, I know some people are very hesitant to run the simulator using on the command line, and that is what is stopping some people from using the trace analyzer. But I'm telling you, I made this tool to help you guys debug your programs. So this is the quote-unquote ultimate tool to really track down what is happening with your program. Okay, so RJ says, using the double pointer, how do I increment the value of PTR? Well, okay, let me just say that one more time. Go back to this here. The subroutine, these three locations, okay, corresponds to what your subroutine has access to directly. Okay, so do not make any assumptions anywhere else on the stack or otherwise. Okay, where the stack pointer points to and the 2 bytes above that, those are the 3 bytes that each invocation of traverse has direct access to. So you access the second argument, which is a pointer. Once you have this pointer, you get to this location. So you first have to use this location where it points to, put stash or byte into that location. And then the second thing you need to do is to change this location and just add 1 to it. So that is what you need to do to increment the pointer itself. And then Joshua said, isn't trace just the disassemble tool in I guess, VS Code. No, it is not. Okay, it is actually those are two different kinds of tools. This assembler allows you to read the mnemonics given the opcode. So given all the binary bit patterns, all the zeros and ones, all the hexadecimal digits, this assembler gives you the mnemonics back. And it would try its best to come up with label names, but typically it would just use some kind of generic label names like L1, L2, and so on. Okay, but if you have a smart disassembler, it might be able to find out that this label is corresponding to the beginning of a loop and so on and so forth. So it might be able to do that, but it doesn't tell you what is going on while the program is running. The trace analyzer does that. Okay, it tells you which register got changed by which instruction on at which memory location. But the best part is, everything is time-based. So if you go to the trace analyzer, okay, each row like this or this is basically telling you what got changed at a particular slice of time. And time goes forward like this. So that means, you have a complete history of how memory locations, flags, and registers got changed during the execution of the entire program. So that gives you, basically all the insights that anyone can possibly need in order to debug a program. Now, just because it's giving you all the information doesn't mean it tells you what the problem is. So you still have to go ahead and analyze the traces, from a program to figure out, where it deviates from what you expect the program to do. So that really is the tricky part, right? Because now you have to come up with your expectation of what should go into each memory location, or which register should be changed to what value by what time, by which opcode, and then you have to compare your expectation to what the trace analyzer is telling you. And if they are not the same, if they deviate, okay, then you have found the bug. Okay, you have found the symptom of the bug, and then the next step is to find out why are they different. Okay, why is it changing this location instead of that location? Why is it changing this register instead of another register? That depends on the actual code. All right, so Joshua has a question. So once I have addressed all the questions for this particular homework assignment, I'm going to start something new. Okay, it's called a pointer to a function. It is actually a part of C. It is not, it's not in C++. It is actually in just regular C, but it's a pretty useful and kind of interesting concept. So I will address all the questions first regarding the homework assignment, and then we'll move on to talk about that. All right, so Joshua says, oh, is it fair to say that it's like the disassemble with a step-through feature of the debugger? Not quite. So the trace analyzer does not disassemble in any way. In other words, it tells you that you're executing an instruction at location 0, at location 1, at location 4, and so on. But it doesn't really tell you what that instruction is. So you kind of have to combine both the assembler, particularly the assemble tab, because the assemble tab can give you the location in column W, and it will also tell you everything that you need to know about that instruction. So it will give you the opcode of the instruction. So increment D has an opcode of DF in hexadecimal, and it is at location 1B. So if you combine the assembler, okay, and the trace analyzer, then you can both read what code is at a particular memory location and what it did eventually. So somehow online, at location 4, the Z flag got set, okay? And that's not really surprising, okay? Because at location 4, if I go to location 4, it is a subtract D from D instruction. Now, it doesn't matter what value I had originally in D. If you subtract register D from register D, it's going to be a 0, right? Because it doesn't matter what D was. I mean, if you subtract the value from itself, it's going to be 0. And obviously the Z flag is going to be set as a result of that. So this is what what I was referring to, which is, combine the trace analyzer and the assembler. So this way, you can use the trace analyzer to kind of okay, the trace analyzer is a time machine. Okay, it allows you to run the code forward and backwards. Okay, and it tells you everything about the registers as they get changed. It tells you everything about the memory locations as they get changed. It tells you everything that you need to know about the flags as they get changed. But the assembler is the one that is corresponding to the actual source code that you put into the program. So you kind of have to combine those two, but not to combine, but to use both at the same time in order to figure out, why your program is not working up to a certain point. In the previous lecture, I also kind of mentioned, how to approach writing this program. Okay, in other words, you have to break it up into small sections. Now, even without the voice, if you just watch the video, you can see how I, in the C code, how I, took just the shell of the C code and then just write a very simple statement. And then I added some more code and then added some more code. So that is the approach to do it, is really to write the subroutine step by step. You don't move on to write something unless you can prove that whatever that feature is dependent on is already working. So you have to move in smaller steps, especially because, between now and Thursday, there are only 2 days. So, anyone who's trying to be too ambitious is most likely to feel the backfire from all of that. Okay, RJ says, help me to think of the trace analyzer as a timeline. Exactly. It is, a timeline of, that records everything as a program executes. And that's kind of something that I have shown and tried to emphasize a long time ago. I guess, most of you just did not have a need to use it. So nobody actually paid attention, or very few people, I should say, no one. All right. Cool. Okay, no problem. All right, so I'm assuming there are no additional questions regarding the homework assignment or how to debug that program. So what I'll do next is to kind of talk about another topic, which is related to C programming, and particularly this is used a lot in C++ in object-oriented programming. Now I know, the prerequisite of this class is only 360 and not 400, so I'm not going to touch that. But I will still touch on things that are related to C because, that is still the prerequisite of this class. So let me go ahead and just, go and write a program in C first, okay? And then we'll translate that into assembly. Okay, so we'll call this program PF, pointer to a function. Okay, and we'll go ahead and write a subroutine. So I'm going to write the first subroutine is using signed integers. So we'll here. Okay, so this way I can use int8 underscore t. Okay, so we'll just use this as a compare function. Okay, so we compare, we can basically compare an unsigned integer to another signed integer, and then use that to tell us which one is greater or, okay, let me, I'm trying to figure out, how to do this. Okay, is less than. There we go. Okay, so it is just returning a Boolean. If the first argument is less than the second argument, it returns a non-zero value. Otherwise, it returns a 0 value. So whether the return type is signed or not really is not important because it is just saying whether it is or it is not. Okay, and here the signedness is useful. Okay, so we have int8 underscore tb, and all this is returning is a is less than b. Okay, that's all. So not very fancy as a subroutine. Okay, so now I'm going to write another subroutine here. Okay, int 8_t, and this one is going to make use of a pointer to a okay, let me change this a little bit here. Okay, these are all pointers. So we are supplying the pointers of the values to be compared, and then dereference the pointers, when it's time to actually do the comparison. So this one is a dummy function. Okay, I just call it dummy, and it has 3 parameters. So the 3 parameters I'm giving this, the first one is the one that is really awkward. Okay, it is a pointer to a function. So this is how we define a pointer to a function. So pfunc is a pointer to a function. So when you specify a pointer to a function in C, you can even specify what parameters it is supposed to get. So we'll say it is expecting 2 void pointers. Okay. And then the actual values to be compared are also pointed to by void pointers. So we have void pointer ptr1, void pointer ptr2. Okay, and this is the dummy function. And the dummy function is, when you look at what it does, is really simple. Okay, it is just returning the value of calling the function the pfunc is pointing to, and it passes ptr1 and ptr2 along as they are presented to dummy. Okay, and then I will explain this as soon as I'm done with main here. Okay, so inside main I have the actual signed integers. Okay, int 8_t, we'll call these xy. Okay, x is -2 and y is 5. Okay, and I just want this to compute. Okay, I just want to call dummy in this case, and I'm passing the address of is less than, and then I'm passing the address of x and the address of y as the arguments, and then return a 0 over here. So it doesn't really do anything useful. So now the question is, why do we have to go through all this trouble? Why not just call is less than directly? Okay, so that is probably a very valid question, is why don't we just call it directly? Why do we have to go through dummy and pass the address of the function of is less than to dummy, and then pass the address of x, pass the address of y, and then having to do all of this stuff here, so in a strange way? Now, this program is not going to compile. Okay, the reason why it's not going to compile is because is less than does not have void pointers as its arguments. It has integer pointers as its arguments, so it's not going to compile. So to make this compile, we'll have to do some additional tricks. Okay, so we have to use void pointers over here. But when you use void pointers and you dereference a void pointer, they cannot be compared. Okay, because the void type cannot be compared. So this is where things get a little bit tricky, because now this is the time when we have to switch it back to integers. So we basically cast the pointer first to an assigned 8-bit integer pointer, and then when we dereference a signed 8-bit integer pointer, that becomes a signed integer 8-bit integer. Okay, so this program should compile. Okay, and let's make sure it compiles first, and then we'll go ahead and explain it. Okay. Yep, it does compile. Okay, so now we go back and explain the content, and vim, there we go. All right, so we'll go ahead and try to explain this program now, and we'll turn on line numbers. Has anyone seen code similar to this? How many people have exposure to pointers to functions? Yeah, okay, great. Ramsey has some exposure. Okay, excellent. Never liked this. Okay. All right, so that's okay. Never seen this. Okay. Well, this is just regular C. Okay, has nothing to do with C++ or object-oriented programming. This is plain old C. But I understand that in CISP 360, there's a lot of topics to cover, and this may not be one of the topics that a professor have time to go over. Okay, so first of all, let's go through line 3 to line 6 first, okay, which is the is less than subroutine. All right, so over here, does anyone have any question about what A is and what B is as parameters? They are basically void pointers. So a void pointer, okay, A and B in this case, is really just saying that, hey, I'm a pointer, I point to some location in memory, and then, but when you ask A and go like, so what kind of things are you pointing at? A says, I have no idea. I am just the address of something, but I have no idea what that something is. Okay, what kind of thing I'm pointing to, I have no idea what it is. Okay, so that's basically what a void pointer is it is just an address of something, but we do not know what kind of thing is at that address. Okay, so when we dereference, okay, we have to first cast A. This is a cast operator. Okay, in case you do not remember, this is a typecast operator, and it is basically casting A into this new type. So instead of looking at A as a void pointer, now we are telling the compiler and say, trust me, I know what I'm doing, okay? And go ahead and treat A as a pointer to a signed 8-bit integer. That's what this operator is saying. Now that this part here, the highlighted portion, is a pointer to an 8-bit signed integer, we can now dereference it. And so when you look at this entire expression, it really is a signed 8-bit integer value, okay? And it is the same thing on the other side. So I'm really just comparing the signed 8-bit integer that A is pointing to the signed 8-bit integer that B is pointing to, okay? So, wow, that's a really long way to check whether something is less than something else. Okay, so I will show you why this is a really powerful technique later on. Okay, so now let's talk about line 8 to line 11, okay, which is the dummy function. So the dummy function is quote unquote dummy in this case because it's just an illustration of how we use pointers to functions and how we pass parameters to a pointer to a function. Okay, but in real life, dummy is no dummy, okay, because there's a quick sort function in C that allows you to sort an array of stuff, okay? So that's really the fun part, okay? Because when you write a sorting algorithm in C, C++, or any language, and it is supposed to sort items in an array, the first question is, what are we sorting? Are we sorting integers, signed, unsigned? Are we sorting doubles? Are we sorting structures? Well, if you're sorting structures, then the next question is, how do we compare two structures? Okay, what field, what members do we use to compare two structures? What makes one structure less than the other structure? So there are all kinds of questions like that. Okay, so that is what the dummy is I don't really care. Okay, I don't really care what you're comparing. Just tell me how to compare. Okay, tell me where I find the first thing and where I find the second thing, and that's all I need to do. Okay, because in terms of sorting, well, okay, in terms of sorting, you also need a few other things. You also need to know how big is each thing, depending on, because you need to copy and you need to move things around in the array when you're sorting. But if I just need to know the order of two things, this is all I need to do. And the Angel is typing. I'm gonna wait until he's done. Okay, so Angel is typing, passing the address of a function and structure, and then comparing. So we're comparing what the pointers are pointing to. In this case, they're only pointing to signed 8-bit integers. The whole point is I don't need to know. The dummy function, the function that is named dummy, does not need to know any types at all. All it says is, tell me where the function is that can do the comparison. Tell me where the first thing is. Tell me where the second thing is. Now I can take care of the rest. This rings a bell about a standard function that let you pass your own function to use for the sorting and comparison. Yes, absolutely. It's called quicksort. I'm not 100% sure whether it's called qsort as a function name. So let's look it up. Yep, it is qsort. Do you see how this resembles what we have? This compar, okay, which is the pointer to comparison function, is taking constant void pointers. Now the const here is basically just saying, yeah, we're not supposed to change what the pointers are pointing to. Okay, so I probably should add const to it too, but since in assembly language programming there's no such concept as a const, it's not as important as far as what we're doing is concerned. This is where the array is starting at. This is how big each item is in the array. And this one is oh no, I take it back. This is telling us how many items are in the array. This is telling us how many bytes each item in the array is taking up. So that is qsort. So qsort is implementing an abstract algorithm without needing to know what types we are dealing with. And that is because the only thing a sorting algorithm really needs to know is how to compare. Now, what about the other stuff? What about this? What about this? And what about this? That is for specifying the array itself, okay? Where does the array start? How many items are in the array? And how big is each item in the array? That's what the first three parameters are for. But the last parameter, which is a pointer to a function, that really is the key, is how do we compare two things within that array. So RJ says this sounds like a nightmare to write in assembly. Oh, no. It's actually pretty easy to do. And then Angel is saying so many pointers. Yes, but at least we're not dealing with a pointer to a pointer. All right. So given all of this stuff here, let's go back to our C program. Okay. And just to make sure that this code is working, okay, so we say int8_t result, and we want to store to result, okay, what we're comparing, just to make sure that it seems to everything is working, okay. Not yet. Well, I mean, double pointers have applications, but I don't use the double pointers unless I need to. So we'll use pf-pf.c. There we go. pf. There we go. All right, so we're just going to put a breakpoint on line 20 just so that we can see what result is. Or maybe, you know, we break on line 19 so we can just single step, okay? So we run the program, we get to line 19, and then we single step into dummy, okay? So you can see how in dummy, pfunc has an address, because nonetheless, I mean, this is an address to a function, but it is still an address, okay? And that turns out to be the address of the comparison is less to, you know, the subroutine called is less than. ptr1 is this thing here, and then ptr2 is this thing over here. So now the question is, are we really sure these are x and y in main? Okay, well, let's double check that. So we use backtrace bt, and then we look at frame 1, which is in main, and then we ask, don't tell me what is x, tell me where it is, okay? And don't tell me what is y, but tell me where y is. So now we can compare, and we can see that x is at an address ending with fe, and that's exactly where pointer 1 is. And then y is at an address that ends with fd, and that is also where ptr2 it really is pointing to. So let's go back to frame 0, okay, which is dummy itself. So now we can single step again, but this time when we single step, this syntax here is saying, okay, let's go to the subroutine that pfunc is pointing to, and call that subroutine instead, okay? So we single step, and not really surprisingly, now we are in is less than. So is less than has two parameters as well. So I'm just passing ptr1 as A and ptr2 as B. But when we get here, we can now manually, okay, do all the typecasting and and dereferencing, and we ask, what is A pointing to? If I pretend that A is not a void pointer, but instead it is a pointer to a signed 8-bit integer, what value is it pointing to? What do you guys think it's pointing to? What do you think this, when I press the enter key, what do you think this print statement is going to print? All right. The value of x, exactly, which is -1, -2. And then we can look at B. It would be the value of y in main, and that's 5. That's how we initialized x and y in main. So this is how the subroutine is less than was able to get back to what main had. Okay, what the local variables of main. Okay, so when we single step, it's gonna end is less than, then it's gonna end dummy. Then we are back to the main subroutine here, where we can print the result, and the result is non-zero because -2 is in fact less than 5. Okay, so this is not very exciting, okay, because we are just going through a long line of stuff just to compare two signed integers. So in the same program, now I can do something that's a little bit fancier. Okay, so I'm going to say struct student. Okay, so each struct is representing a student record of some kind. And a student has first name, last name, and so on, right? So we can have like a char first name, and we can give it like 32 characters. I know I'm supposed to use a constant for all of this stuff here, but this is not the important part. Okay, I'm not going to sort or compare using these. This is what I'm going to use for comparing. GPA. Okay, so but as a structure, okay, there's no inherent way of comparing two student structures, okay? Because you can always say, are we sorting by first name? Are we sorting by last name? Or are we sorting by GPA? Okay, all three is possible, right? And what if two people have exactly the same first name? Then what do we do? Okay, well, we sort by first name first. If there's a collision, then we sort by last name. So now the question is, how do we specify that logic? Okay, so now we have a function, okay, just like is less than. It returns just an 8-bit signed integer because it's really just a boolean. But we can now call this student is less than, okay, and we have two void pointers again. Okay, because if the subroutine has a non-void pointer, then we can no longer pass it into dummy. Now there are ways to cast the address of a subroutine. Okay, so let's go ahead and do that. Okay, because I want to play with that too. So we say this is a struct student. So that means we don't have to do a lot of typecasting inside the subroutine, which is good. Okay. All right. So in the subroutine, let's just say that we are only comparing the GPA. So we basically now say, A's GPA is less than B's GPA. All right. So this is how I want to compare two student records. Is really just to look at the GPA and see if the GPA of A or the GPA of what A is pointing to is less than the GPA of what B is pointing to. Okay, Angel has a question. I'm gonna wait a little bit until he's done typing. Okay, both Eugene and Angel are both typing, so I'm going to use this opportunity to do some initializations here. All right, Angel's asking, then you make an else for when they're the same. Not exactly. I just need less than in order to compare. So less than is all we need. Remember the discussion in our class, because if you have less than, you can use that to define greater than, less than or equal to, greater than or equal to, and not equal to. Overload less than operator. Yes. So this is what leads to the concept of overloading in C++. Now, overloading an operator really is cosmetics. Okay. In other words, it's really just using operators that we are familiar with, and then instead of using a name of a subroutine to do the same thing. So as far as I'm concerned, operator overloading, even though it is a nice feature, all it really is cosmetics. All right, so I have a student record here, and we'll call it tag. Okay, and I'm just going to go ahead and initialize it. Okay, because it has got first name. So first name is tag. I'm not sure whether it would take a null terminated string like this, but we'll just assume that it does. Okay, and I have a GPA of 2.0. Okay, and then struct student Dave Fox, right? So this is Dave Fox, and he has a GPA of 3.999. No one is perfect. Close. Okay, there we go. All right. So now we want to call dummy again. Okay, so we want to get the result of comparing the two student records. Okay, so now we go, okay, let's take the address of student is less than, and then we'll pass the address of tag as a student record, and then pass the address of Dave as a student record, and it should be able to return a non-zero because my GPA is less than the GPA of Dave. All right, so we'll go ahead and say, okay, let's go ahead and compile this. And then the compiler chokes on this because it says, okay, now this kind of message takes a little bit of getting used to, but basically it's complaining about student is less than as a function, does not use void pointers as its own parameters. Okay, so that's why it is choking, and it does not like this. Okay, so how do we fix this? The answer is there are two ways to do it. One way is to go change the definition inside student is less than. That's one way to do it. So we have to change A as a void pointer, and then change B as a void pointer, and then we have to cast A and B as struct student pointers before we can access the member of the structure that they point to. Okay, so that's one way to do it. But this way is very, very cumbersome. Okay, and casting a void pointer to something else is always kind of dangerous. So let's try a different approach. Okay, in other words, let's try to cast it over here and say that, let's look at student is less than as a pointer, as a pointer to a function that is of a different type. Okay, so we'll go ahead and type in what that thing is. So it is an int8 underscore t, which is the result type, and it is a pointer to a function. This is how we specify this is a pointer to a function, and the arguments or the parameters of the function that this pointer is pointing to are both void pointers. Okay, all right, so I know this looks kind of super awkward, okay, but when you look at it, okay, it does have a consistency with what we know about the syntax of C. Okay, this is the return type. Okay, this one here, so the really, really important part is when we put parentheses around something that has an asterisk, that pair of parentheses is special. Okay, it has meaning on its own, because what that means is we are now talking about a pointer to a function. Okay, so the highlighted portion of the text of the program here is where the compiler gets the idea of, oh, we are not talking about an unsigned 8-bit integer, we are now talking about a pointer to a function that has a return type of 8-bit signed integer, and these are the parameters of the function that this pointer is pointing to, and they're both void pointers. So instead of casting inside the subroutine, I'm writing the subroutine student is less than just kind of normally, but I'm casting the pointer to the function to what dummy is expecting. Okay, and I think this should work. Okay, let's give it a try. Yay! All right, so now we want to see whether it is working or not, right? Because we want to see whether it is returning a non-zero value, because my GPA is less than the GPA of Dave. Okay, so we'll go ahead and check it out. And we don't have to stop on the first line, so we're going to put a breakpoint on line 34. So we run the program to line 34. We single step into it. Okay, so the first single step is not very exciting. All it does is to confirm that, yep, we are using student is less than as the comparison function. We are using the address of tag as a student record as the first pointer. We're using the address of Dave as a student record as the second pointer. So that part is not very exciting. When we single step again, now we get into student is less than. But when we get to student is less than, because I did not specify a void pointer for A or B, I can now actually say, tell me what is the record that A is pointing to. So I can say you print asterisk A, and it tells me that, oh, it's a student record, first name is tag, last name is Young, and then the GPA is 2.0. Tell me what B is pointing to. Oh, B is also pointing to a student record. First name is Dave, last name is Fox, and GPA is 3.999. So when it's time to single step line 12, which is comparing the GPA of what A is pointing to, and that is 2, against what the GPA of what B is pointing to, which is 3.999. So we are now saying, oh, okay, it's a double precision floating point number comparison, and the values being compared are 2 and 3.999, and 2 is less than 3.999 is true. So when we single step, this ends student is less than. We single step again, this is ending dummy, and now we are getting back to main. Now we can say, okay, what is the result? It is also non-zero because we're comparing 2.0 versus 3.999. Okay, so the program does work. Okay, and what I want to illustrate, or the importance of this code, or the understanding of this code here, is dummy is the same. Okay, now dummy is very useless in this case because all it is doing is to return what pfunc is returning. Okay, what the function the pfunc is pointing to is returning. So it's not particularly useful, but on the other hand, you can make a dummy a little bit more useful. Okay, so let's say so I'm going to change dummy to be slightly more useful. Okay, so what I want to do is to say is different. Okay. Given only a function that can tell me whether something is less than, now I can express equal to, it's different, not equal to, as pfunc ptr1 ptr2 or pfunc ptr2 ptr1. In other words, if whatever ptr1 is less than ptr2, or whatever ptr2 is pointing to is less than whatever ptr1 is pointing to, then those two are different. Okay, I consider those two things as different. So now it's starting to become slightly more useful, because it doesn't matter whether pfunc is pointing to an integer less than function, a struct student less than function, or any type of less than function. This logic still works because being different is really the same thing as less than or greater than, and that's how this type of approach is going to work, is going to be useful. So do we have any questions about why this particular discussion is useful? No questions? All right. Or have I lost the whole class? All right. I haven't lost anyone. I have not lost everyone. So there exists at least one person who is not lost. Very good. And Angel is typing something. All right. You're not going to forget, which is not to say that if I ask you specifically what you learned on the day, you can remember that. But next time, when you move on to a, let's say, object-oriented programming class, you will start to look at C++ in a different light, okay? Because what we have here in this program is really how we do abstraction that C++ is also doing using classes and all the different types of member functions and whatnot. Okay. All right. So while I'm waiting for Angel to type his stuff, I'm just going to change the program a little bit here to use is different. Okay. Just so that the program will continue to compile. And now we're going to ignore this line, okay, and translate the program without using structures, because the whole point is, how do we implement something like this, okay? How do we deal with a parameter that is a pointer to a function? So we use this to compare structures, not functions. We're passing the address of a function in order to compare structures. All right. So let's go ahead and see what is different as a subroutine is going to look like in assembly. So we're only focusing on is different here. Okay. And obviously, is less than, can also be switched to use the other approach, which means I'm not using void pointers here, and I'm casting the address of the function while I pass it to is different. Then we cast it at that point. Okay. But that's not really the important part. The important part is, how do we do this function here? So we'll go ahead and do a for yy, and then I will use a different file for the ttpasm. Okay, oops, right first, and go to, there we go, and then paste. All right. And this is the really cool part of using syntax highlighting, using my rules, and using basically anything that is Vim based. Is if the syntax is wrong, it's going to highlight it to really, tell you that, hey, something doesn't look right here. Okay. All right. So we'll now go ahead and start to write the actual code. Is different is a label. And it has got three things on the stack, right? Because we have got ptr2, ptr1, and then pfunc, and on top of that, we also have the return address. So I'm going to say is different id underscore return address is 0. And then the pfunc is 1 byte on top of that. And then we got ptr1, which is 1 byte on top of pfunc. Oh, okay, specify ptr1. And then we got ptr2, which is ptr1 1 plus. I forgot about the 1 plus over here too. There we go. Okay, so return address, pfunc, ptr1, and ptr2. So everything looks good. All right, so now the question is, how do we get this to work? Okay, and Joshua is typing something. I'm keeping an eye on Discord. Do both structs and objects behave this way? That's a very good, interesting question. A struct is not exactly an object. Something that you use a struct to make is an object. So structs are more like a class. So a struct is like a class where all the members are public. Okay, so let's work with this one. Okay, So we have to call the first one first. Okay, so we're going to call with ptr2 as the second argument and ptr1 as the first argument. So this part is no different from what we already know how to do. Okay, so what we are going to do is to do LDI A and an ID ptr2 because that's the first argument. Add AD. So now A has the address of ptr2, and then we do LDAA. So that register A is now the actual value of ptr2. Then we push it on the stack. Okay, so we decrement D, allocate 1 byte on the stack, and then stda. And then we do something like this with ptr1. So we do LDIA again, ID ptr1. But this time we need a 1 plus because we got 1 extra item on the stack already at this point. So that's what the 1 plus is doing, is to compensate for that 1 extra byte that is already on the stack. So now we say add AD, LDA A again. So A is now ptr1, decrement D, stda. So now we have pushed ptr2 and ptr1 on the stack. So now here comes the third question. How do we make use of the function that pfunc is pointing to? Well, before you can get to the function, you still need to get to pfunc on the stack. So same idea, okay? LDIA, ID pfunc 2 plus this time, because we have got ptr2, which is an extra thing on the stack, ptr1, which is another extra thing on the stack. So the way we find pfunc is now 2 bytes away from the where we would otherwise have found it at the entry point of the subroutine. Okay. Otherwise, same deal, okay? Add AD, LDA, A. So now A is just pfunc, which is the pointer to a function. So here's the interesting part is, how do we call that, okay? Because JMPI obviously cannot do it, because JMPI can only jump with an immediate, which means it has to be determined at assemble time. This is something that can only be determined at runtime. Okay, so let's worry about this later, because we still have to push the return address. So we use the usual typical thing, but this time I have to use register B because register A is still useful to me. I cannot clobber register A at this point. So I'm going to use register B and then 1 5 plus, which is specifying the return address. std. We're going to go back and fix this a little bit, okay, because that is the wrong place. So normally we have JMPI to some label, right? But this time it's not JMPI, it's just JMPA, okay? And because it's not a JMPI, the number of bytes is going to be a 4 instead of a 5. So when we get back, we are now back to here, and then we have to increment D twice, increment D, to deallocate the arguments. Okay, all right, so let's just kind of pause here for a little bit and try to figure out what just happened over here. Decrement D we kind of get, okay, because in order to push anything on the stack we have to decrement the stack pointer. Okay, fine. And then over here we have LDI register and then .4 plus instead of .5 plus. What is going on here? So LDI itself, takes up 2 bytes. So if I use comments to indicate how many bytes or what is the offset of certain things, this is offset 0 and offset 1 from LDI itself. This is offset 2 from LDI. This is offset 3 from LDI. And this is offset 4 from the LDI instruction. That's why we have a 4 here, because where I want the subroutine to return to is 4 bytes away from where the LDI instruction is on this line. Okay, and the reason why it's not 5 is because JMP only takes 1 byte instead of JMPI taking up 2 bytes. And JMPA is something that we have seen already. Every time we return from a subroutine, we just JMP and then whatever register. Okay, typically we use B because A is used as a return value, but in this case I'm using A because that's where I put the address of the subroutine that I want to call. So is that okay? Does everybody kind of get a general idea of how to call a function indirectly in assembly? I don't see any feedback. Does anyone want me to finish this code? Okay, so I jump to the address loaded in register A. That is correct. Register A contains the address of the subroutine because register A has the value of pfunc. Very good. All right, so I'm just gonna finish this code because there's a second half to this. Okay, but before we get to the second half, remember this is a logical OR, which means if pfunc is returning non-zero at this point, I'm done already. Okay, so we should double check that. So we can say and AA, and we say JZI to second call. Okay, otherwise we can do a JMPI to the end of this subroutine. So we can JMPI to end sub, and then end sub is defined over here. Second call is defined over here. All right, so the second call is going to be very much like the first one. So I'm just going to be a little bit lazy and copy and paste a bunch of code here. So we'll go ahead and start with line 12 and stop here. And then paste. And then we just have to change all the PTR1 to PTR2 and all the PTR2 to PTR1. VI gives you, a way to do this without having to do it manually. But I'm gonna do it manually for now because to do it the other way needs a little bit explaining too. And this is really fast because I just got like 4 lines that I need to change. So PTR1 becomes PTR2, PTR2 becomes PTR1, and the call is happening here, the allocating is over here, and then whatever the second call is returning is going to be my actual return value. Because if the first one fails, it returns a 0, and then the second one also fails, then we have false or false, which means the result should be a false. If the first call is a false, the second one is a true, then whatever the second one is returning is also what I want to return as my own value. So that means I don't have to do any checking whatsoever with the value that the second call is returning. So at this point, I just have a regular return, which is LD B, because I don't want to mess up A anymore. A actually has the correct return value. So LDBD, increment D, JMPB, and that concludes the implementation of just the subroutine called isDifferent. Okay, we are running out of time today, so I don't have a chance to actually test run this to show that this code works. But in terms of concept, this code does capture all the concepts that we have talked about. So Q-sort is an interesting thing. Before I end today's lecture, I do want to point out why Q-sort is useful, because Q-sort, okay, as a C function, you can see from the header file that includes it, it is part of the standard library in C. In other words, you can use GCC, you can use Microsoft C compiler, you can use any C compiler, and it should have Q-sort implemented in this library. So Q-sort, once again, is a very useful function because it can sort an array of anything. Okay, so the 4 pieces of information that you need to give Q-sort in order for Q-sort to work is to tell it where is the beginning of the array that you want to sort. You have to tell it how many elements are in that particular array, and then you have to tell it what is the size of each item in the array. And then the last item is you have to give it a function to compare items in the array. So int here is actually going to return so the comparison function, which is compare, in this case, must return an integer that is less than, equal to, or greater than 0 if the first argument is considered to be respectively less than, equal to, or greater than the second one. So it's kind of the same deal as string compare. Okay, string compare also returns negative, 0, or positive value depending on how the two strings compare. So that's all it needs, is to have a compare function that can return, that somehow can relate two items in the array that you're passing to qsort. So that makes qsort really useful because you can have an array of integers, okay, and you can sort it. You can have an array of student records, qsort can sort it too. You can have an array of students, and the first time you want to sort it by last name, and then later on you want to sort the array by GPA, and then you want to sort it by student ID. All you have to do is to change the address of the function compare, and it will sort it using different criteria. And that is why being able to pass the address of a pointer to a subroutine is really helpful. It really helps to abstract things in plain C. Now, C++, being an object-oriented programming language, has a lot more different mechanisms, better, quote-unquote, better mechanisms to do abstraction. But when you're writing code, strictly in C and not C++, this is a great way to do abstraction so that you can use the same base code regardless of what each thing really is and how to deal with the thing, as long as you can pass, quote-unquote, the method as a pointer to a function. All right, so I think that pretty much concludes today's lecture, and I'll leave it up to you guys to kind of work on your program. I will stay on the chat channel for the next hour and a half or so. So if you have questions, you can go ahead and direct message me, or you can use the general text channel. I can only answer questions that are specific, so I cannot really help you guys debug in the sense that somebody send me the code and go and ask me what is wrong with the code. I cannot help with that. On the other hand, if somebody has a question of my program is only working up to this point, or it seems to be in a loop, if the symptom is well described, I can try to diagnose those issues. All right, so that's it for today, and I will talk about the solution on Thursday. All right, I can see people signing off and no additional questions. So I'm going to sign off from the voice channel as well and stop the live stream.